All right, so that's a quote-unquote easy one. The reality is it's not easy if you don't think it's easy. So I call something easy if it's comparatively easy, easier than a similar problem with a different structure. Find the area of the region bounded by y equals the natural log of x, the x and y axes, and y equals 3. Right? With respect to the x-axis, with respect to x or with respect to y. All right, well, this is, if you weren't motivated to, I feel like that video didn't take. I'm just really thinking about it. When I put my hand in front of it, yeah, it definitely didn't. All right. One corresponding number. There would be one intercept point, but we do have a natural bound. They told us that we're going out to y equals 3. So that's going to cap it off somewhere. So when we create the graph, here's the natural log of x. Under normal circumstances, it looks something like this. If you don't know that, y equals, type in ln of x, zoom 6, take a look at the picture, see what's up. All right. It has an x-intercept at 1. And it's telling us to go out to y equals 3, which I'm just going to ballpark. I'm going to pretend that that's y equals 3. Now, a logarithmic function increases without bound, but its rate of increase decreases, which means that it's very steep early on, but then it shallows out. All right? It's kind of like the growth of a human being. I mean, that's actually a logarithmic function. You start off with a set height, like when you're born. You don't start off with a height of 0. Right? You start off with a height greater than 0. And then you increase dramatically in height early on and weight. But then as you get older, I mean, I haven't increased in height in like 20 something years. Right? So if I have, it's been like by like microscopic amounts. Right? And in fact, I'm probably going the other way at this point. I don't know. Because you start talking about spinal conditions and compression of the spine, people start actually shrinking in height because gravity takes hold and it sucks and it's painful. But without getting too much into that, the idea is that human growth would follow a logarithmic model, not an exponential model. The other way would be that your rate of increase is actually increasing, which would be fun to watch, but it wouldn't be fun to live through, I don't think. All right. Like, what was the character from Willy Wonka, the one that turned into the giant blueberry? Violet, thank you. So, area bounded by ln of x, the x and y axes, and y equals 3. All right, well, here's the y-axis, here's the x-axis, poor quality, let me do that again. Here's the log function that's relevant, and here is the part of the line that's relevant. So they're talking about this region in here. So, honestly, I feel like I want to change the problem a smidge. I'm going to make this or. It's the first time I've changed it in 15 years, 20 years, whatever. Only because the whole point behind this is for you to determine which method is more convenient. To make you do it both ways, it feels like it defeats that purpose. Right? So you decide. Is it better to integrate with respect to x? So vertically oriented rectangles with width along the x-axis, or with respect to y, which would be horizontally oriented rectangles with width along the y-axis? Which is better? The y, yeah. Partly because I'm asking the question, right? So it's like reading the teacher kind of thing. But also, the entire region is contained between the curve y equals ln of x and the y-axis. If you look at it from the perspective of the x-axis, you got a little issue here, because on this interval, it's the line that's bounding the function, and then from here out, it's the natural log that's bounding the function, and that won't even give you the part that you want. All right, so what we're going to do is look at it from the perspective of y. All right, so I'll just draw kind of a shell of the graph. The shell of its former self. Zoom it in. Draw horizontally oriented rectangles. Call that dy. It's got a length x, but x as a function of y. All right. It's a slight little thing in terms of notation. I'm writing x of y. Some people are just fine writing x. I'm fine either way. But if you write it as x of y, it's a nice little reminder to yourself that what you're looking to put in there is an equation, not just the variable x. All right? Because otherwise you have the same function every single time, and it's like, what are we learning here? All right? This goes from 0 to 3. So my general form for this area would be on the interval of 0 to 3, I'm looking at x of y dy. All right, now just going back to this function here is y as a function of x, ln of x. I need it solved for x in terms of y. What's x equal to? I think I might have heard it. No, 1 over. There was an e in there. I heard an e. E to the y, you got it. All right, I'm going to pull it off on the side and show you, just in case you didn't know. If you wrote this natural log as log base e of x equals y, all right, that's the same thing. ln just means log with a base of e. All you're doing is converting from log to exponential form. All right, so how does that look? Well, there's a couple of schools of thought on it. The way that I think is most popular, it's not my favorite way, it used to be, would be to take the e, raise it to the y, and set it equal to the x. A little circular motion going around. That's fine. If you know the names of each part, life becomes a little bit easier, because you have log with a base of e of x equals y. All right? When you have an exponential function, you have a base raised to a power equals a result of some kind. It doesn't matter what it is. All right? The base of a log and the base of an exponential function are always the same, or the corresponding exponential function. So if I know that the base of a log is 2, then I know the base of the corresponding exponential function is going to be 2. Then it's just a matter of getting the placement right. So one of these values, x and y, is going to be the exponent. All right? So all you have to do is a quick switcheroo on these two variables and you have it. All right, so e is going to be to the reverse. And the idea of reversing things, it should make sense, because when you're talking about inverses, you know, the natural log and e to the x, or e to the y in this case, they are inverse functions of one another. So inverses, I mean, the definition of inverse, regardless of how it's applied, really just represents switching, you know, reversing things. All right, so if you've gone through the process of converting from one form to another without reversing something, then you probably did it wrong. All right, so what I have here is x equals e to the y, but I can also write that as x of y equals e to the y. The reason why I'm mentioning that, you wouldn't have to write that, is so that you can realize that it's the e to the y that's getting plugged in here. Now, aside from making something that was more complicated in terms of how many integrals you'd have to use to come up with the area, you know, it was 2 separate integrals and then a subtraction from a rectangle if you had to do it in terms of x. Here it's just a single integral. Okay. A byproduct of that, which we're never actually going to see in this problem because we chose the easy way out, is that in the process of doing this, you would have had an integral containing the natural log of x. All right? Now, we're allowed to use calculators, so that's not a problem. But if you weren't, flash forward to Calc 3, and you have somebody who's not of a similar mindset as me, it makes you use a by-hand approach for everything. It's like, calculator, what calculator? Some of you know what that feels like. That's why you're here. So if that's the case, you come up with an integral that has a natural log of x in it, and you look at it and say, ah, yes, the antiderivative of natural log of x. I will be staring at this problem for quite some time because I do not know that piece of information. It could be a problem. You need to, if you don't know the rule, you'd have to use integration by parts to figure it out. All right. Obviously, we're not there yet in this course, but even if we were there, it's not something you want to do. The antiderivative of e to the y is e to the y on the interval of 0 to 3. So we're looking at e to the 3 minus e to the 0th, which would be e to the 3rd minus 1. You might be surprised to hear this, but that was the first time somebody did not shout out 0 for that one. If you were thinking it, there's no shame in that, but anything to the 0th power aside from 0. 0 to the 0th power is indeterminate, but if you raise a non-zero value to the 0th power, the result is always equal to 1. It's a subtle little mistake that crops up from time to time. It's the kind of thing that you don't want to fall into, but I mean, personally, it's the kind of thing I'm destined to fall into at some point. Those little careless mistakes where I'm just not thinking. All right, so I'm going to do the same thing with the next one. And these are typos. I mean, you'll see the complete solution in the completed notes from last semester. You'll get it from both respect to x and with respect to y, so you'll see what it's like to look at it from both viewpoints, but I think it makes more sense. I mean, still reflecting on things after 20 years, 19 years. I think at long last I've come to the realization that this just makes more sense to do it this way. Find the area of the region in quadrant 1. Quadrant 1. Pay attention to words in a problem. Otherwise, you find yourself doing more work. Bounded by x squared plus y squared equals 8. All right, that's a circle. Not a very convenient radius, but something we could live with. X equals 1/2 y squared, and y equals 0. All right, knowledge of functions come into play here. And conic sections, as it turns out. We're dealing with a circle, so center at 0, 0. I mean, you draw it any way you want, as long as that center is at 0, 0. It's a nice, crappy circle there. Look at that. Look at that piece of nonsense. All right, that's our x squared plus y squared equals 8. X equals 1/2 y squared. That is the inverse of a parabola. How do I know it's an inverse of a parabola? The x and y values are switched. That's how you find inverses. Oh. One of the no, that was a joke. She actually she had to get her knee drained. It was horrible for her. I mean, I was fascinated. I'd never seen that before. I didn't think a needle could go as far into a knee as that. I was like, well, glad I'm not you. That's terrible. It's these kind of moments where I know that she doesn't watch any of my videos, because I'd have all my stuff waiting on the front yard. But it's all right. Anyway, sideways parabola, because that's how an inverse parabola looks. Right? Parabolas, if they're sideways, they're not the entire parabolas. They're not functions. They would fail the vertical line test. So there'd have to be a plus or minus there. It would have to be piecewise in order to actually get the entire sideways parabola. So if it's only the positive, that means that it has to just be the top half. All right. So I'm going to do something along these lines and go from there. Now, okay, so maybe you don't recognize that immediately. Maybe you do. Some of you do. I try not to make too many assumptions when it comes to that sort of thing. But let's say you didn't. If you didn't, there's an avenue, right? If we have an equation that has y's and x's in it. All right, so let's work with the y's and x's. So x equals 1/2 y squared. Double both sides. 2x is equal to y squared. Square root both sides. Y equals plus or minus the square root of 2x. You chuck this into your calculator and you see what's going on. All right, I promise you that this is what you're going to get, especially if you consider the fact that it said quadrant 1. See, I was focused on the fact that it had to be a function. But quadrant 1 kind of makes that a moot point anyway. All right, so that gives me the positive part. All right, so there's your bailout. You don't recognize what a function looks like? Your calculator is there for you. All right. Sometimes it'll take a little longer, but it's time well spent if it helps you get the right answer eventually. And you know what? Honestly, all wisecracking aside and all that stuff, the reality is you're still learning through the process. During a test, if you take the time and you're like, all right, let me put that in the calculator, let me see what it looks like. We've all had these moments. You hit graph and you're like, oh, of course it looks like that. Duh, I knew that. You're just reinforcing something that you already knew. It's a process of learning, so it's still a good thing, all right? So it's never a waste of time if you're learning something. Anyway, I need to find the area bounded by the circle, the sideways parabola, y equals 0. So that little wedge there. So this little slam-a-lama ding-dong here. Now it's all over Facebook. Oh wait, no. No, it's not. Because they're quote unquote friends. But you don't use Facebook, right? Nobody does. It's all like people like me and stuff. I don't post anymore because people post like quotes of things. Like, oh, what was the one? It ain't no bed of roses. It's no pleasure cruise. I'm like, I don't know what you mean by that. I mean, I know it was part of a Queen song, but like, what are you getting at? Like, please stop. So, anyway, that's what that was. It was not a video of my son performing, unfortunately. Anyway, so I gotta find this area. My choices are with respect to x, in which case I'm bounded by this curve on the interval of here to here, wherever here is, and then I would transition over from here to here. But that would be a new curve, all right? Because it's the sideways parabola followed by the circle. Fine, I guess. Nothing wrong with that. If I go with respect to y, it's the difference between the two curves. I can write that out right now, all right? I would have to solve this equation for one variable in terms of the other, but that's not difficult. But I still need to know where to stop, right? Because if I'm doing it with respect to y, I'm starting at 0 and then working my way up until I get to this intersection point. One way or another, I need to know what this point is. All right. Now, the good news is it's not a bad deal because you could do it on the calculator like we did before, but this one's actually even easier because I have a direct substitution. In the process of solving for y in terms of x, I actually came up with an equality between y squared and 2x. So if I wanted to, and I do, I can find the intersection between these two equations, which is going to give me x squared plus, instead of y squared, 2x, that's my substitution, equals 8. X squared plus 2x minus 8 equals 0. And then I could solve that. You pick your method on that. You could factor, if it's factorable. Is it factorable? If you see it right away, go for it. If not, go to the calculator. All right, so plus 4 minus 2. All right, so it would be, you got two solutions, x equals -4, that's not relevant. X equals +2. All right, so we have a 2 as the x value. So then I just need the corresponding value of y. Y is equal to the positive square root of 2x. Which is also 2. So I now have my intersection point, intersect at 2, 2. All right. So one way or the other, I have everything I need in order to figure out that bounded region. We'll do it with respect to y because that's generally, in my experience, the thing that people need the most practice with. So if I'm doing it with respect to y, I'm looking at the difference between the outer function, which is that circle, all right? But I need it as a function of y, x as a function of y. So I'm going to take this equation and solve it for x in terms of y. All right, so x squared is equal to 8 minus y squared, making x equal to, normally again, it's plus or minus the square root of 8 minus y squared, but it's only the right part of it, right? It's with respect to y, so it's right side, left side. Left side negative, right side positive. If it were with respect to x, it would be top side positive, bottom side negative. All right, right side, top, positive, left side, bottom, negative. All right, so I have that function. Then the function that is the non-dominant would be the x equals 1/2 y squared. All right, so I'm looking at the square root of 8 minus y squared minus 1/2 y squared dy over the interval of 0 to 2. And that would be your bounded area. Find the area of the region bounded by y equals e to the negative x, the axes, and the line x equals 3. I'm going to kind of cut to the chase on this and just give you the quick sketch. This is what e to the negative x looks like. Your calculator can easily tell you that if you didn't know. And in reality, it doesn't look anything like that. That's just the way I draw it. I mean, it's very steep early on, and then it levels off, but it should look gorgeous and smooth, and mine doesn't. All right. So we have the line x equals 3. If I wanted to find the area of this bounded region, it's just a continuation of what we were doing on the previous page. And what I would do is first decide, does it make more sense to work with respect to x, that's a typo, or with respect to y? And so, based on the quality of the drawing, you might have a little trouble deciding. In this case, I think it's pretty cut and dry because you have the bounded area entirely contained by the function and the x-axis. All right, there's no change in function over the interval. If you did it with respect to y, on this first interval here, so going from 0 to whatever this intersection point is here, the bounded area would be contained between x equals 3 and the y-axis. But then once you get to this point and go upward, it's now bounded by the curve and the y-axis. All right, so two separate integrals would be necessary, or, you know, an area of a rectangle and an integral, but two separate calculations necessary to figure it out. Whereas if you do it with respect to x, I can create an arbitrary rectangle over this interval, and no matter where I draw that rectangle, it's always going to span the distance from the x-axis to the curve without interruption. All right? So ask yourself that question when you're deciding. Can I draw a rectangle from my chosen axis to the curve, covering all the area without any kind of interruption? All right, the answer here is yes. So now I know it's appropriate to make this a dx situation because my thickness of the rectangle is along the x-axis. All right, its height is determined by whatever y is, but y as a function of x. So when I define my integral with the relevant variable of x, it's happening over the interval of x equals 0 to 3. The y of x is this guy right here, e to the negative x. All right, and now we just plug and chug in the calculator. Math 9, 0, oh, I hit enter too quickly, go 2, 0 to 3, e to the negative x dx, about 0.95. All right. But again, what I was saying before is if you can't conceptualize what the best approach is, sometimes it might come down to the quality of your diagram. So for me, if I'm looking at this and be like, I don't know which way to go, I might consider redrawing my diagram so that my exponential curve didn't look as god-awful as it does. And then it might be a little clearer what I'm up against. All right. Maybe sometimes just looking at the calculator display as opposed to a hand-drawn picture does the trick. All right, so a little what-if question here. What if emerging from the area you calculated were infinitely many squares? I feel like I updated this. I feel like it did it for the other class. Okay, well at least it's the same one. All right, so emerging from the base area were infinitely many squares forming a three-dimensional solid. And I'll say base area as described above were infinitely many squares forming a three-dimensional solid. Forming a 3D solid. And I guess a question mark would make sense here. We're racking up the typos tonight. Good for you. Good for you. I think there's 2 people already maxed out on typos, yeah. Already got their 3 points. So that's good news. Now, I don't know, if you think about it, I'm giving you 3 bonus points per unit test. Gave you 3 bonus points for the YouTube subscription, and I'm giving you 3 bonus points for typos. What are we up to, 15? That's a lot. You're welcome. All right, so, I mean, we rephrase the question. That's all well and good if you don't know what the hell it means, right? So, let's draw a diagram. Nice y-axis there. The y-axis I drew like that on purpose. For some reason, with perspective drawings, I have trouble with the horizontal lines for some reason. All right, so we're creating a perspective drawing where the y-axis is on a slant. So we're basically creating the illusion that it's a three-dimensional diagram. All right. Well, it is a three-dimensional diagram. It's just not a diagram that's in 3 dimensions. All right, so x, y. We had the line x equals 3, which would have to be parallel to the y-axis, because once I draw the vertical line, or the vertical axis the way I do, or the way I did, any other vertical line would be relative to that, so they'd all have to be parallel. All right. Now, in terms of the curve, all bets are off. There's only so much I can do here. So that's my y equals e to the negative x. I mean, I was basically gifted a passing grade in studio art in 9th grade, so you take what you can get out of this. All right, so this corresponds with the diagram from that quote-unquote do now problem. That shaded area, quote-unquote shaded area that would have been shaded if I actually shaded it in, will now be the base of a three-dimensional solid. All right? So what we're going to do is create infinitely many squares that are going to emerge from that base. All right? So they're going to basically jut out of your paper. So if you were actually to draw that graph on an XY plane, put it down on a desk, and then take pieces of cardboard, really, really thin pieces of cardboard, because it's supposed to be squares, not actual prisms, and then place them vertically on that paper, and then get infinitely many of them in there, so infinitesimal width, so the width approaches 0, but the number of squares approaches infinity, then what you would create is a solid that is actually emerging from this base area. All right, so this is your lawn. The solid is the grass growing out of the lawn, right, but in a very particular way. So how do we draw it? Well, I'm going to create a square, the base of which is going to be parallel to the vertical axis. And then I'm just going to give it kind of a perspective look. So it's going to look like a rhombus because we're looking at it from an angle. All right, so that's what one square would look like. I'll shade it in. Now, I chose to draw mine there. Maybe you draw or drew yours here. In which case you might have this square. Someone else might have drawn theirs here. In which case you have this square. And yet another person, I'll get rid of the white and go with the orange, may have gone all the way to the end and drawn theirs here. Now I'm only going to ask you to draw one cross section, so you don't have to worry about that. But I'm just trying to give you a sense of what we're up against here. All right? Now, if I were able to squeeze infinitely many squares in here, what would happen is you'd have a little ridge here going from vertex to vertex to vertex all the way through. And so I can create that. And then you have all of these verticals that amount to the side. And this is essentially what your figure would look like. But then when I do all that, it looks like garbage, so unless you squint, like a lot. Like a lot, yeah. It's not gonna fly. All right, so what we're going to do, well, I'm going to get rid of all that crap. And I'm just going to focus on one of the squares. I'll go back to the red one. All right. If I could find an expression that represents the area of an arbitrary square over the interval, then all I have to do is integrate it from the beginning of the interval to the end of the interval, and I'll have the volume of the solid. All right, so it's still going from x equals 0 to x equals 3. All right, so what I need is the area of a square. Oh, it's base times height, but more specifically, it's a square, so it's side squared. All right, so I just have to find the length of a side. Okay. Well, here's a side. That side is actually the only side we could actually it's the only side we could figure out. Because I wouldn't know the vertical side without knowing the base length. All right? So whenever you're talking about the distance from the x-axis to a point in space, its value is y. Whenever you're talking about the distance from the y-axis to a point in space, its distance is x. So this distance going from the x-axis to anywhere is going to be y. All right? Or y of x if you want. But it's ending up at this location here. Right here. That location, I'm going to highlight it, or draw an arrow to it, is x comma y, but specifically x comma e to the negative x. All right, so we know the y value associated with that particular x value. All right, so I now know that this distance, yeah, we'll call it y, but that y is really e to the negative x. All right, so I have the length of the side. E to the negative x, if I square it, I have the area of the square. I can clean it up if I want. E to the negative 2x, power to a power, multiply the powers. All right. So, something else to consider. If I were to actually take a piece of cardboard, like gesturing at the table, you have the graph on the table, you have a piece of cardboard, can you actually have a piece of cardboard with no thickness to it? Of course not. But you could have it with infinitesimal thickness. All right. So if I bring this graph in again and create some thickness here, I get a square slice, a square cross section. That cross section, which is perpendicular to the x-axis, is going to have a thickness along that x-axis. All right, infinitesimal distance along the x-axis, dx. All right, so that reinforces something that you probably already suspected, that we're going to integrate with respect to x. This is the driving force behind it, though. All right, if I came up with a dy here, based on orientation, if I were going the other way with respect to y, then all of this stuff would have to be converted over into equations in terms of y. Different story. All right? So that tells me that if I take the area of the face of one of those squares and multiply it by dx, what I'm going to get is the volume of a square prism. But I'll only get one of them. I want all of them. So I integrate every possible square prism volume over the interval of 0 to 3. All right, the integral is the collection of infinitely many of these square prism volumes over that interval. All right, every single one of them that could exist gets computed and added together, and when all is said and done, you get the volume of the solid with no gaps. All right? It accounts for every smidge of distance on the interval of 0 to 3. Everything that could exist is accounted for just based off of that interval. So, what does that mean? It means if you can come up with the area of the face of one of the cross sections, then you have it. Because you slap on a dx and integrate and call it a day. All right? But sometimes that's the challenge. If you can't come up with that area, then it could be a little bit of a problem. So looking at the second one, or number 1, base of solid S is the region enclosed by the graph of y equals the square root of the natural log of x, the line x equals e, and the x-axis. If the cross sections of S perpendicular to the x-axis are semicircles, all right, so not squares anymore, but semicircles, then the volume of S is going to be what? All right, so we're going to do the same thing. Square root of the natural log of x. Now, composite functions are what they are. If you know what a root function is and a natural log function, you could probably figure it out. If not, you go to this. I'm pretty sure I know what it looks like, but I'm not going to take the chance. I'm just going to type it in. Yeah, it's actually what I thought it was. All right, so here's my y-axis, here's my x-axis. All right, so it's enclosed by that curve, the line x equals e, so that would be this. We have x equals 0 here. And we have to have semicircular cross sections. All right, so I'm going to follow a similar idea to what I did up there, except I'm going to create semicircles. So, a little line segment here, nice little arc. Something like that, I guess. I don't know. Maybe a little bigger. I'll go a little bigger on it. A little thicker. All right. Now, I'm streamlining the process here because although it's really nice to draw something that looks aesthetically pleasing, it's not necessary for the solution of the problem. You just need one cross section to get the job done. All right. I do like to shade it in though, because sometimes, honestly, it has nothing to do with getting credit or no credit or whatever, or just being picky or even, I don't know, making it look nice or anything like that. It has more to do with the fact that sometimes, you know, like with those M.C. Escher drawings, like optical illusions, sometimes I just lose it. Like, I lost the perspective. I can't see it. Like, it looks like it's flat, and I can't make it look like, in my mind, like it's jutting out of the paper. But when I shade it in, it always looks the right way to me. So that's a me thing. It doesn't have to be a you thing. All right. So I'm going to give it a little thickness. So that means I have a dx here. I know that this distance here, because the distance from the x-axis to a point in space is always defined as y. But specifically, we know y is equal to the natural log of x. So we're good there. All right. Now, a circle, the important characteristic of a circle would be, or two characteristics would be center and radius. So we know that the center is somewhere, but we don't really care. Because when we're finding area, you don't need to know what the center is. The radius, I also don't know that directly, but I do know that the diameter is equal to y. So diameter equals y. Diameter is equal to 2 times the radius. So the radius has to be equal to 1/2 of y. Specifically, 1/2 of the square root of the ln of x. All right, so area of a semicircle, pi r squared over 2, would be pi times 1/2 the square root of ln of x squared over 2. So little housekeeping here. A half becomes a quarter, the root goes away, so pi over 4 ln of x over 2. That's going to give us pi over 8 ln of x. Do you need to simplify that? No. Like, you could have left it like this if you want, because it's all going, if you need a number, it's all going in the calculator anyway. All right, so what does it matter? All right, so I have the area of the semicircle. Now what I want is the volume of the semicircular slice, which would be that area, that face area multiplied by the thickness. So pi over 8 times the ln of x dx. Okay, so we got that. I just need another piece of information and I'm good to go. If I integrate, if I want them all, I'm integrating not from 0. Yeah, this is x equals 0, that's the y-axis. But the bounded area doesn't start till this location. Which is where? X equals what? Where's the natural log across the x-axis? 1, yeah. All right, so we're going to go from 1 to e. 1 to e pi over 8 times the ln of x dx. Then the volume is, okay, so I have to put it in. It doesn't say write a function that represents the volume. So math 9, 1 to e. Second division, if you didn't know that, you get just the e. So pi over 8 times the natural log of x, close paren, x, 0.393-ish. I'm kind of glossing over that, the calculation part, because there's not an overwhelming expectation that you would attach too much meaning to what this number means. What 0.393, is that a big volume, a small volume? I don't know. Like it isn't until you get into the science of it that you can really investigate that. We don't even have any units associated with this. So it's more important that you come up with the integral than it is that you come up with the number. I mentioned this earlier, and I'll mention it again tomorrow. I'm mentioning it now. I'll get you with the integration later in the next unit. All right. For now, setting up the integral is the main focus. All right. Don't be surprised when you take the test if there isn't more than like 2 or 3 questions that actually ask you to find actually evaluate an integral. All right. Most of it is all the theory stuff. How do you come up with the integral? Now, for some of us, that's like terror inspiring. Others, it's music to our ears. Right? It depends on strengths and weaknesses. But at least you have an idea of what you're supposed to focus on, and that's what I'm trying to get at. Right? So